Late 40s.
Yeah, so they're still young, right? Yeah, you all will pray for them, and yeah, inshallah, everything will be. Yeah, these exams and um, simultaneously. And yeah, but be brave, and in the end, Allah will yeah, make things right. Even
Inshallah, sir. Thank you.
everything now. So yeah, let us start right. What is physical? This is the thing that we did in the last. And let me again make this diagram, because this diagram, if we understood this diagram, then this chapter will be very advanced, right? So let us make this diagram again. So what do we have? We have, so we know that what is photoelectric effect, right? Photoelectric effect is when the light of uh, certain frequency falls on some surface, then the electrons get ejected off, right? So that will be it. So light of yeah, so electrons gets ejected, and that phenomenon, because that emission of electron is happening due to the light. So that is why it is called photoelectric effect, right? So there is this beautiful setup that that is used to understand all the natures of this photoelectric effect, right? And yes. So first, what do we have? We have this discharged tube made up of quartz glass. So why we are calling it discharged tube? So there is nothing inside this tube, right? Not any gases. So this is a vacuum tube, and made up of this is made up of quartz glass, right? And this is the discharged tube, right? Yeah, this is a discharged or vacuum. So why this is discharged? Because there is no any other charges, right? There are no any other charges. So then we what we are doing is that we are keeping this thing open, right? And light can enter from here. So let's say this is the source. Let's say sun, and light is entering from this part. Now we want to catch this light on some surface, right? Because photoelectric effect is light falls on some surface. So we want to make this light fall on some surface, and that we call, let's say this plate is called a C. So this plate should be photosensitive, right? This is a photosensitive plate, which where the light falls, right? So this is photosensitive plate. Now we have another plate, right? Which is so now the light are falling on this plate, so electrons would be ejected. Now if the electrons are going here and there, so we cannot collect that electron. So what we are doing is that we are providing a potential, so that, because let's say this is positive potential, this is positive potential, this is negative charge, so this potential will attract these charges towards each other, so we can collect those charges, right? If we don't have this plate, then these electron will go here and there. So now we want to create a potential so that these charges gets attracted and it falls on this plate. So this would be called This plate would be called the collector plate, right? And this is, let's say, A plate. And then we can supply some potential onto this plate, right? So let's say, the this one falling like this one, and then we have this one, and it goes like, and then from here we connect the potential. So we can measure. Let's say we have connected a microammeter. So this measures the current in a microampere because the amount of current would be very small. So we have made a microammeter, right? And then we also connect a voltmeter to check the voltage across A and C, right? And then what we can do is that we can also make a rheostat, right? So that we can change the potential, right? So we can change the potential through this device. This is the whole setup. And what we can do is that this part is called a commutator, right? So this is the commutator. So you guys will see that what is the use of this commutator. So let's say this is a part, right? This is A part and this is C part. So if I connect this C part to this area, so then this would be connected with the negative potential. So then C will have negative potential, right? And A will have positive potential. Now let's say I want to make this A potential as a negative one. So I will connect this A to this part. So I will connect this A to this part, then it will be negative, and then this C would be positive. So so you can see that if this A plate is negative, right? If this A plate is negative, then what will happen to these electrons? Will they come at this surface? Will they reach this surface if this is negative? Yes, guys. Somehow I make this A potential to be negative. Firstly, what I did, I made this potential. I made this potential to be positive. So this positive plate was attracting these electrons, emitted electrons, right? Now I have changed this commutator by the means of this commutator. I have changed the polarity of this potential, and this has become negative. So if this is negative, then what will happen to these electrons? They would be repelled, right? They would be repelled and they will not come here, they will fall on this surface, right? This is now positive, so this electron would be attracted here, right, guys? Clear?
Yes, sir.
Yeah, so by means of these experiment, we study the behavior of because these electrons are getting ejected due to this photoelectric effect. So these electrons would be called photoelectrons, and then due to this we will have a photocurrent, right? So this photocurrent, if this electron reaches this circuit, then the circuit is complete, and then it will have some current. So that current is called a photocurrent. And that photocurrent, so we see the behavior of that photocurrent, right? So we study this photocurrent by changing, first we change the intensity, right? Photocurrent variation with intensity. So what we do is that let's say some amount of rays were coming, but we increase that much amount, right? So then the intensity would be larger. Then we again increase that amount. So then the intensity would be again larger. So we change the intensity falling on this, right? We make this area small, we increase the area. So then we can change the intensity falling on this plate. So first we can do is that we can change the intensity, and then we can also change, so let's say this these photons, or not, I should not say now photons. So these light rays have some frequency, right? So then I also can change the frequency of this light. So let's say I I uh, I make a filter around here, right? I put a filter around here, so then I can make a bright light. I can make a red light fall on this surface. I can make a green light fall on this surface. So red light, let's say I put a red polythene, right? So red polythene will filter out all the other colors and only red color will pass, right? Let's say I make a blue polythene in here. So then only blue color light will fall on this surface. So in this way, I can also change the frequency, right? Because different color lights have different frequency. So I can also change the intensity. I can also change the uh, frequency. And what else I can change? Guys, what else I can change? Yeah, I can also change the potential around this plate. So I can change the CA potential, right? So these are the three things I can change. So one is intensity, the other one is the frequency, and the third one is the potential at C and A plates. These are the three things that we have to understand. What is it? Oh, I am got so yeah, these are the things that we have to understand. So first, let us understand about the variation with intensity, right? So I want to study the variation with intensity. So what are the parts I'm going to fix? I will be fixing the frequency of this incident radiation, right? I will be fixing the frequency. I will be fixing this potential also, right? So at a constant frequency and potential at C and A, we see that photocurrent varies linearly with intensity. Right, so graph is what? Graph is like we have this. This is our intensity, right? And this is our photocurrent. And this is how the photocurrent is varying. So we can see that this photocurrent is directly proportional to intensity. So this is the first thing that we observe. From this setup, this is the first thing that we observe. So this photocurrent is dependent upon the intensity, right? This is one thing. Second thing that we observe, so variation with frequency, right? Or let's say variation with potential at C and this is the second. So what we observe that let's say this is the potential at A. So collector potential and this varies like and this is our current. And then other variation is this the other variation. So now you guys can ask me that why? Because this is the potential, right? And this potential is at A. So how this potential is becoming negative, right? You guys can ask me that. So as I have said you guys, that we can change the polarity, right? We change the polarity of this A potential and then this can be negative. And then we increase the amount of potential. So you guys can see from there that if I increase the negative potential, then let's say that some potential at this point is of let's say 5 joules energy, right? And let's say that the light are falling on this thing and the energies of different electron is let's say 5 joules, 2 joules, 7 joules, let's say 1 joules, and the potential that I have set on this A is 4 joules, right? So let's say the potential at this point is 4 joules. So which two one will cross this part and which two electrons cannot cross this path? Which two will cross? Which two cannot cross?
What do Jasola pass?
Yeah, so 7 and 5 will pass, right? Because they have higher energy. They are emitting at higher energy, right? But this 4 joules, so these 2 joules and 1 joules electron, they would be repelled by this potential, right? So what will I see that? And now I am increasing this potential. So now I'm increasing the potential and subsequently increasing the energy. The repelling energy I am increasing. So this would be, let's say, 6 joule and then it would become 8 joule. So if it becomes exactly, let's say, the highest energy of the electrons which is getting emitted is 7 joules. So if I increase the potential at 7 joule, so will any of the current will fall on this circuit? Any of the current will fall on this circuit? No, because I have set it to the maximum value. So this would be repelled, right? This would be repelled and no electron will fall on this surface. So if no electron is falling on this surface, then what would be the current? What would be the current? The circuit is not getting completed, right? What would be the current? Yes. What would be the current? Zero. So photo current at this 7 joule, at this 7 joule, the photo current would be zero. So this is what we are seeing in this graph. So we have increased the potential, negative potential, and let's say this is V naught. And at this V naught potential, the current is, this is the photocurrent, y-axis. So y-axis, this is becoming 0. Photocurrent would be 0 at this potential. So this is called stopping potential. This is stopping potential. And these are, so at these three different graphs, the current is becoming constant, right? Let's say if I choose this graph. So this point, the current is becoming constant, right? And then if I increase the potential, then the current will remain the same. So this potential, this current, this highest current is not dependent upon the potential, right? So this would be fixed. So these maximum current, these are called the saturation current. So these are called saturation current, right? And we can see that we can increase the value. So these are three different values, three different saturation current. This one is the highest saturation current, right? But these are for different, because I have fixed the photosensitive plate, right? I have fixed the photosensitive plate, and then I have also fixed the frequency. So then this saturation current is only dependent upon this intensity. So this one is I3 intensity, this one is I2 intensity, this one is I1 intensity. So I3 is higher than I2 is higher than I1. And these are what? Intensity, right? So now you guys can tell me from this graph that what is the thing which is depending upon intensity and what is the thing which is not depending upon the intensity. Yes, from this graph, can you guys tell me what is dependent upon intensity and what is not dependent upon intensity? Yes, what is dependent upon intensity, what is not dependent upon intensity? Okay, what is same for all of the intensity? What is same? What is different for all of the intensities? What is same for all of the intensity? Can you guys figure that out? What is same for all of the intensity? Oh, so someone has replied in chat. Photo current. Oh, so you see, Maria, photo current is changing. Photo current is changing due to different intensity, right? That we have already seen. That photo current is dependent upon intensity. So I'm talking, okay, so let me just rephrase my question. So you have two parameters. One is saturation current, the other is stopping potential. These are the two parameters. What is dependent upon intensity? What is not dependent upon intensity? Yeah, what is changing, what is not? Yes, guys. Because all the answers are there in that graph. All the answers are there. E, E. Yeah. So photo current is G. Yeah. So I mean to say saturation current, right? The saturation current is changing for different intensity potential. You guys can see the stopping potential. This stopping potential For this I1 intensity, this is same. For I2 intensity, this is same. For I3 intensity, that is also the same, right? So the stopping potential is not dependent upon the intensity. Saturation current is dependent upon the intensity. So that is what we take out from this graph. Is that clear?
Yes.
Is, so let us write these two things, right? So one thing that we understood is saturation current. Highest photo current that can pass through the circuit even frequency and different collector potential is called saturation current, right? So this current saturates. You cannot increase the current any further. So that is called saturation current. And also we can say that when all the electrons, or I should say photoelectrons, are collected at the collector potential, then it is called saturation current, right? And saturation current is dependent on what? This is dependent on what? Potential or intensity? Yes, saturation current is dependent upon intensity, right? So this is about saturation current. Yeah, intensity. Absolutely correct. And then we have B part is stopping potential. The highest negative potential at which photocurrent becomes zero is called the stopping or cutoff potential, right? And it is equivalent to, so it is equivalent to the highest kinetic energy of the emitted electron. I should say photoelectron. And so the example that I gave in here, that what you are doing is that the photoelectrons are emitting out from the surface, and let's say that highest kinetic energy of the photoelectron is how much? 7 joules. And you have provided the negative potential to this 7 joules. So then all the photo current will not pass through this circuit, so they will be repelled out. So you will have zero photo current, right? So that criteria is called the stopping potential. So at stopping potential of the, so it is equivalent to the highest kinetic energy of the emitted photoelectron, right? Which is given by Ke max. This should be how much? EV naught. This is a very important relation, right? And this stopping potential is independent of what? Dependent of what, guys? This is independent of intensity, right? So we saw from the graph that we change the intensity. So we change the intensity. But for all of these intensity, stopping potential was same. So these are the first two analogy observation we take from this setup. So you guys please note it down, and then we will yeah. So please note down this diagram, and then we'll talk about the third and last property. So you guys please if you guys have any question, please tell. Yeah, and whenever you guys want me to scroll down, please tell. Yeah, whenever you guys want me to scroll down, please tell.
So can you please scroll?
Yeah. So whenever you guys want me to scroll down, please that.
Sir, can you please go? Done, sir.
Yeah. Then please also topic. Yeah, this is stopping.
This already wrote.
Oh, you have already written. So what about you guys? Aisha and me. What about you guys? What is? Yes, Aisha and me. What about you guys? What is? One minute. Okay, yes. Yes. Right. So only if we have understood the graph, then everything would be clear, right? If we have understood the graph, then everything becomes clear. So in the second observation, what we are doing, we are fixing the uh, frequency, right? We are fixing the frequency and then we are changing the potential and intensity. These are the two things we are doing.
Okay.
Yeah. Now in the third experiment, what we do is that we will fix the we will fix the we will fix the intensity, right? We will fix the intensity and we will vary the frequency. So that so third is variation with frequency. So there are two variations. One is obviously the photo. One variation is this is our collector plate, which right. And you guys, so this is obviously the photo current. So in this part, what did we do? In this diagram, we fixed the frequency and then we changed the intensity. Now what we will do is that we will fix the intensity and then change the frequency. So what happens is that if we have fixed the intensity, then this thing would be same, right? So this thing would be, let's say this is, and then we will have this thing, and then we have, so this is the saturation current. And we have already understood, right? This is our saturation current. And we have already understood that this saturation current depends on what? This saturation current depends on intensity.
Mhm.
Intensity, right? It is not dependent upon potential. But these are the three different frequencies. So let's say this is one potential. Let's say this is V naught 1. Let's say this is V naught 2. And let's say this is V naught 3. Right? So these V naught 1 has a new 1 frequency. This has new 2 frequency. This has a new 3 frequency. So you guys can tell me, right, from this graph, you guys can tell me that the saturation current is independent of this frequency, right? All the frequencies have a same saturation current. What is changing? What is changing for this? What is changing for this frequencies? What is changing?
Mhm.
Yeah, stopping potential is changing, right? For different frequencies, this stopping potential is changing, right? So this is one thing that we understood. And the other thing is that if we right, if we make the graph of frequency, right, and stopping potential, this is V naught. So at first point, this is negative, but as soon as it reaches some, let's say V naught V1, right, V1, then it goes linear. And let's say this is one metal, and then we have another metal also, right? So for another type of metal, this is again linear, and this is metal B, but this is happening at a different frequency, right? Let me write it as V naught, and this is V naught 1, this is V naught 2, right? So for this one, this frequency, right? This frequency V is greater than this V naught 1. So if nu is greater than nu naught 1, then this stopping potential is linearly varied, right? And if this nu is greater than nu naught 2, then stopping potential is linearly varied. But at this point it is 0, right? These are the two things. These are the two observations from different graphs. So what we can say? We can say that stopping potential is dependent on the frequencies of the photosensitive material, right? So frequencies of the incoming radiation, right? And second thing is that it varies linearly with frequency after achieving or for a minimum threshold. I should not write a threshold. I will write about this later. But for minimum certain, these are it varies nearly with frequency after after a minimum certain frequency. So these are the two observations we make from these two graphs, right? So for different kinds of metal, it is different. These are the two things that we understood. So please note down this part and then we will write overall result. Please note it down and then we will write the overall right. So please note it down. So in three steps we have done our observation. First step was that intensity was varied, frequency potential was fixed. In the second step, we varied, we kept the frequency fixed, we varied intensity and potential. In the third step, we kept the intensity same, we varied the potential and this frequency. So these are the three things we have done.
Done, sir.
Done. Okay, then please note down these two observations. And from these observations, we'll write a summary of the experiment. Yeah, whenever you guys have noted it down, that.
Done, sir.
Yeah. So now let us write this. What is this? First, what did we understood? That for a given frequency and potential of the photoelectric material, the photocurrent is directly proportional the intensity of incoming radiation. This is the first thing that we understood from first observation. And second thing that we understood that for a given frequency, the saturation current is directly proportional to the intensity of the incoming radiation, whereas the stopping potential, why do I write as stopping? So stopping potential or kinetic energy, maximum kinetic energy, is dependent or independent. Right? First, we will write or let us write dependent on the frequency of the right first that it is independent. First, we write the independent part, independent of intensity, and then we will write the dependent one. So then, for a given intensity, now we are fixing the intensity. There is a minimum frequency before which photo photoelectric emission does not happen, and that frequency is called the threshold frequency. So when the light or when the incoming radiation has an has a frequency greater than threshold frequency, then photoelectric emission happens. And the maximum kinetic energy is dependent on the frequency of incoming radiation. Right. So this is the third one, and the last one is that the emission or photoelectric emission is an instantaneous instantaneous process. It takes 10 raised to power minus 9 second to emit the photoelectron. Right, so it whenever a frequency, whenever a certain frequency greater than threshold frequency falls on the surface, at at instant the electron ejects. Right, so at instant the electron gets ejected. So it doesn't take some time to reach some stage and then it is ejected. No, it instantly ejects that electron. So let's say the frequency of let's say 500 hertz falls on this surface and the threshold frequency is let's say 200 hertz, then instantly this electron will eject, right? So that is the idea of this photoelectric emission. So you guys please note down this part, and through the observations we understood these things, right? Now you guys can write the things without any confusion. So please note it down. We have discussed all these things, and this is the conclusion that we make from that observation. Please note it down, and then we'll move on to the yeah. Whenever you guys have noted and you want me to scroll down, please. Yeah, whenever you guys want to slow down, please tell.
Done, sir.
Yeah, then please down. Yeah, whenever you guys have completed this.
Done, sir.
Yeah. Okay, so these four properties of photoelectric effect, right? All of the properties we can justify, but this third one that we require a threshold frequency to emit that electron. This cannot be justified by the wave theory of radiation, right? We have understood that interference, diffraction, and polarization, all these effects, but we cannot explain this phenomena, photoelectric effect, using the wave picture of light. So then Einstein told or stated that we should not think of these radiation to depict these or to justify these photoelectric effect. We should not think the light or the radiation as wave nature. We should think of the light is made up of some tiny particles, which he called them photons, right? So photons have a quanta of energy, so its energy is quantized. Quantized meaning that we can write it in small fractions, integral multiple. So energy is quantized, and from that picture, he gave the idea of photoelectric effect, right? So these were all observational results. So then he gave a theoretical picture of this photoelectric effect, right? So first thing that we observed that the wave theory cannot explain the photoelectric effect. So then Einstein gave the particle theory of radiation, in which stated that light is made up of tiny particles called photons, which have discrete energy, right? So this is what he stated, and then he gave this idea of photoelectric effect. So according to Einstein, right, he said that the kinetic energy maximum of the photoelectric particles that would be equal to the light falling, right, and then some work function. So the light, if we have, so you can see that this kinetic energy is related with the stopping potential. So stopping potential is related with this frequency, right? It is not dependent upon the intensity. So all the explanation that we wanted from photoelectric effect, that was single-handedly, right? So this is a very beautiful expression. This is a very beautiful explanation that from this single equation, we can justify all those four effects from this single expression, right? So we know that kinetic energy should not be negative, right? Kinetic energy, because we cannot have some energy which could be negative, which means that to have an ejected electron, have an emission, we should have h nu greater than phi naught, right? So if we have this condition, then we will have some kinetic energy of the photoelectrons, right? If we have overcome this, so this is called the work function, right? So the minimum energy we require to overcome have the photo emission, right? To have the photoelectric effect, we require minimum energy to overcome. So this minimum energy is called the work function, right? And this mu is the frequency of incident radiation. And so let's say we can also write this kinetic energy as h nu minus h nu naught, right? Nu naught is the threshold frequency. So we can write this thing as what? So kinetic energy max. This should be h nu minus nu naught, right? So if we have a frequency which is equal to threshold frequency, then kinetic energy would be zero, right? If we have a frequency which is less than this kinetic energy, less than this threshold frequency, then we cannot have this photoelectric emission. And if we have a frequency which is greater than this threshold frequency, then we will have photoelectric emission. So this equation explains every criteria of the photoelectric effect, right? And we also know that this kinetic energy is related with the stopping potential. So this stopping potential is also related by this h nu minus phi naught. So we can write this potential as h nu by E minus phi naught by E. So we can see that this potential is varying linearly with this frequency. So V naught is directly proportional to this frequency. That is what we saw from here, right? So that is this graph. So all these graph was explained, beautifully explained by this Einstein photoelectric effect, right? This is the beauty of this Einstein equation. And Then we saw the particle nature of radiation, right? So this is the one thing. We will do some question at some later point. But you guys please read about photons, right? That is given in the NCRT. Please read about photons from NCRT. That is your right NCRT. Please read about it. That is very simple. That photon is made up of so radiation is made up of tiny particle which is called photon. Photons have certain energy and yeah, they have certain frequencies. All these things are written over this. Please read that part, right? And then, so now we understood that this radiation has wave nature. This radiation has this particle nature. So radiation has this dual nature. That part we understood. So then T. Broglie thought that is this possible or is this the same case for the matter as well? Because we know that the matter is made up of electron, proton, and neutron, right? So matter is showing the particle nature, right? So can matter also show this wave nature? Because for the case of radiation, we saw that radiation is showing in the diffraction, interference, and all this refraction, it was showing the wave nature. And we also see in the photoelectric effect and Compton effect, we see the particle nature of this radiation or light. So is the matter also show this wave nature or not? So then T. Broglie gave this hypothesis that from that he predicted the wave nature of matter, wave nature of matter, and that was shown by T. Broglie hypothesis. This is a hypothesis, but this is proved by the observation also, right? So hypothesis. And you guys will understand the theoretical explanation in your higher classes. But now, yeah, so he just gave this hypothesis. And from this hypothesis, he told that the wavelength is the wave nature, right? Wavelength of the matter that would be related by h by p, right? So this shows the wave nature of matter, and momentum is particle nature, right? So this h by m, right? So then he gave this theory that this wave of, so let's say the particle is moving with some velocity, so it will carry some momentum, and that momentum will be related by this wavelength. So this wave nature is shown by this T. Broglie hypothesis, right? So this is the last topic of your dual nature of radiation and matter, and there are several questions depending upon this, right? So we also know that this this velocity, right, or this lambda. So this lambda we can write it in terms of what? We know that E is h nu, or we also know that this is hc by lambda. So we can write this lambda, right? We can write this lambda as hc by E. So we can write this thing in here. So hc by E, this is h by p. So we can cancel this thing out, and c by E, that would be 1 by p. So energy would be how much? This would be Pc, right? This is another thing that we. So this is for radiation, right? This is for radiation. So from this way, we can also show the wave nature of matter. These are the two things that we understood. Wave nature of matter, particle nature of radiation. This was all about this chapter. Please note down this part. And there are questions that we so we'll do some questions. Okay, you guys have please note it down. And if you guys have any questions, please join. You guys please note it down. And whenever you guys have noted it down, please. This chapter was very simple, right?
Yes.
Yeah, noted, Aisha, you have noted. Yeah, whenever you guys have noted it down. Oh, okay. Yeah, so I guess
That's all.
yeah. Then please this is for long, right? For yeah, whenever you guys have noted it down, please. And next class we will start. But we will start the atoms and nuclei. Yeah, whenever you guys have noted, please. Got disconnected. Yeah, whenever you guys have noted it.
That's
Okay, so yeah, we'll start.